Flip on the back. We're just going to recap real quick the 4-step process. Okay? The first step was to state the parameter. Nick, I know it's exhausting, but we haven't really done that much work. State the parameter we want and how confident do we want to be. All right, that's just reading the question. It's usually stated in the question. Name the procedure. So this is the plan step. Name the procedure. Right now we only have one. It's the 1 proportion Z interval. And you can abbreviate it, that's fine. The conditions or assumptions, do you remember what they were?
Random and large count.
Yeah, random sample. And we got to check that it's normal using, in this case, large counts, okay? So those are the 2 conditions I have to check. General and specific formulas, plug the numbers in, calculate the interval. This is all you really have to worry about is writing your formula with your values in it. Obviously, you're going to use a calculator to crank it out, right? And then calculate your interval. So this is the do step, where you actually do the math. Show your work. State, plan, do, and then we conclude. This is where we tie a little bow around the problem and put it back in context. Yes, bows. Yes. It's a little package, right? It's a whole package problem, start to finish. So, can we handle that? Yeah. I should record this. A community activist group in Austin, Texas wanted a particular issue to be placed on the ballot of the upcoming election. To make it on the ballot, 20,000 valid signatures were needed. The group turned in their petition with 24,598 signatures. To pass the validity test, 81.3% of the signatures must be valid. It's too time-consuming to check all the signatures. So a random sample of signatures were checked. The individual checking the signatures need to be 95% confident that the true proportion of valid signatures are estimated with at most a 2% margin of error. All right, so right here is where they're giving us the desired margin of error. They're giving us E. So you just got to remember, when they give you E, they'll probably give it to you as a percentage. You got to make it a decimal. Are you allergic to this skill set, Dylan? Sounds like it. All right. So it says, using a conservative estimate, how large a sample is needed? So what the heck does that mean? What's the conservative estimate? .5 is considered the conservative estimate, by the way, for your p-hat value. When they don't give anything else, we use conservative. All right, so we're going to use this equation. So n equals z star. Conservative estimate is 0.5. 1 minus 0.5 is obviously 0.5. And the error desired is 0.02. Now, does anybody remember what... 0.02 squared. I forgot the squared. Anybody remember what the z star is for a 95% confidence interval? Good. 1.96. I need to calculate. All right, 1.96. So let's come over here and plug that in. 1.96 times 0.5 times 0.5 divided by 0.02 squared. All right, let's put this in the calculator. Is it supposed to be squared on the formula chart and I just didn't write it down? Yeah. It is? Okay, I knew something was up. So it's z star squared. Sorry about that. had 2401. Y'all get that? Okay, so what does that represent? 2401 what? Signatures that need to be sampled for validity. Okay, so you would make sure you put it in context. 2401 signatures. Now this is a random example that came out to be a whole number that rarely happens, but there it is. All right, so let's try the next one. In the activist group's previous petition, 85% of the signatures were valid. Using this valid as a guess for p hat, so that means we're not going to use the conservative estimate anymore. Find the sample size needed for a margin of error of at most 2 percentage points with a 95% confidence. How does this compare with the required sample from part A? All right. So now we're using a p hat of 0.85 instead of 0.5. All right, so let's plug in our values into our formula. 0.85, 1 minus 0.85 is 0.15, all over 0.02 squared. Let's see what we get here. I got 1224.51. Anybody else get that? Yeah? Okay. Okay, so I would not leave my answer like this because you don't want to leave it in decimal form. You can't survey half a person, right? So we round it up, so it'll be 1225 signatures. All right, how does this compare to what we got in A? Huh? It's almost half the amount, right? So this is where, if you have a percentage you can work with, it's better to do that because that's fewer samples you're going to need to take. The conservative, like what we use on A, is always going to be bigger than reality you really need. But as we know, that's a good thing if you got nothing else to work with. All right? So it's definitely going to be smaller when you have a real estimate to use. What if the company demands a 99% interval instead of 95%? We're not going to calculate it. Let's just think about this. If it was a 99%, what part of my equation would change? The z-star. Anybody remember what my 99% was? It's kind of a stretch. I'll just tell you. It's 2.576. So that z-star would be 2.576. If we use all the same values, just think for a second, is that going to end up with a bigger number or a smaller number? What do you think? I'm going to calculate it out and see. We're dividing by the same amount, right? But the top number is going to be bigger, isn't it? Came out bigger? So it's going to end up with a larger sample. Okay, let's think about that. Larger sample is going to give us bigger confidence, isn't it? Do you remember that little applet I showed you with the little arms? If we increase our sample size, don't our arms get smaller? So that makes sense, doesn't it? We're going to be more confident. We're going to have a smaller margin of error. So it's going to give us a larger sample. All right. So far, so good? That's what it looks like if it's a proportions question. So let's jump. Let's look at the back. Let's just summarize this. So when you do an interval for a mean, you state the parameter and the confidence level. So it's always going to be the true mean something, whatever the question says. True mean number of states, true mean height, true mean weight, whatever. the plan step, it's a one sample t interval for mu. You don't necessarily have to remember that, but you do have to know these two. Conditions, and TW calls them assumptions. But it's the same idea. You have to check for random sample, and then you have to check for normal. So this is a throwback, chapter 7. You may not remember this. With means, there's 3 ways you can know it's normal. CLT is our favorite because it's the least amount of work, right? However, if the population is normal, that is one way you can know. And then here's your CLT thing. And then here's if the off chance of these two not working, you have to look at the sample distribution, like a box plot. Or there's a thing called a QQ plot that I'll talk about in the video. And you can just glance at them and know, is there strong skewness or outliers? If there's not, then it's normal enough. That's all it is. Okay, and those displays will be given to you on on a test or something, because I don't want you taking time to draw them out for that. But you have to look at it and you have to make a statement like, the sample distribution shows no skewness or no outliers. You're good. All right, and here's your formula that we just talked about. All right, so let's try this. See if we can do one. City council member wants to estimate how many pounds of trash households in their community produce per week. To determine an estimate for the standard deviation of the weight of trash produced, a small random sample of households was selected, and their trash was weighed on a garbage day. This produced an estimated standard deviation of 36 pounds. All right. Now, on part A, we're going to skip that because this is really section 8.4. We're going to come back to that tomorrow. Okay. So it's asking us how many households do we need to sample. We haven't done sample size yet. That's in tonight's video. So after solving part A, the city council realizes that it'd be too much work to weigh the garbage of that many households. They give up their hopes on estimating the true mean weight produced within 3 pounds, and they select a random sample of 15 households, and they weigh the trash for each of these households on a garbage day. Here's the results. This is going to make us do all the work, all right? But it's not bad, I promise. Calculate and interpret a 95% confidence interval for the mean weight of trash of all households in this community. So we're going to walk through the state plan do conclude thing. I'll show you what you need to show for full credit when you do one of these. And then we'll be done, all right? So in the state step, what am I looking for? Mu. It's the true... I'm just copying the words from the sentence above, honestly. Mean weight of trash for all households in this community. And I want to do it with 95% confidence. That's all you got to tell me on state, all right? On the plan step, what I'm really looking for are the assumptions, okay? So let's see, was it normal, or random? Was it a random sample? Yes. Yes, it was random, and n was equal to 15. Is it normal? Do we know? They didn't tell us population is normal, did they? Can we use central limit theorem? Sample of 15. So that's a big fat no, right? Wah, wah. So now we got to do the worst case scenario. Make a box plot, make a display, whatever. Easiest way to do it if you're doing it by hand is just make a dot plot. Trust, okay? I'm not going to ask you to do this on every question. In fact, most of them I give them to you. It's good for practice. Okay. So if I was doing a dot plot, a dot plot. I said it right. Okay, so let's look at the data. What's the lowest one? 26.5, maybe? So make that 25. Oh, 19? Is there really a 19? Ooh, 19.8, okay. And so that's the lowest, and the highest would be, is it 119? Okay, sheesh. Okay, so let's just make that 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. And this would be pounds of trash. All right, it's only 15 dots. It's not like 50 or 100. We can do this, and you're just estimating here, okay? So that's pretty much there. 74, 80, 99, 31, 93, 118, 88, 46. Okay, so there it is. It's pretty boring, right? Pretty flat, pretty boring. So what I do in this case, after I've done my dot plot, I would just make a little statement. I would say the sample data shows no strong skewness or outliers, so it's safe to proceed. Safe to proceed. And I have completely run out of space, didn't I? All right. On the do step. All right. I need some values, right? I need the average, and I need the standard deviation of this. So I'm going to need to enter this data in my calculator in a list. Do you remember how to get to your list? Stat edit. Okay, my lists are full, so I'm going to have to go up here and clear them out. I'm going to enter those 15 pieces of data in here. Okay, do you remember where to go from here? If I want the average of this data and the standard deviation, where would I go? Huh? Calc? Yeah. How do I get to calc? Stat, over to calc, and then the very first thing, the one variable statistics, okay? And it should say list one, that's what I want. And here's my data. Now, X bar is what I want. So I'm going to write this down. X bar is 68.85. And then I need S. So my standard deviation is the S value, not the sigma, but the S. So 35.78. And I'm going to use those values to plug into my equation. So what do I have? 68.85 plus or minus something T star Now, I'm doing 95% confidence, so while I'm in here, I'm going to do my inverse t. Okay, inverse t would be 4. All right, and I want 0.025. How many degrees of freedom would this set have? N is 15, so degrees of freedom is 14. It's just minus 1. So 14. Boop. So 2.14 is my t star. Okay? And it's going to generate for me, let's see what we get here. 3. Gives me 49.09. .61. All right, so there's my interval. All right, so then the only thing left I have to do is my conclude step. So I'm going to have to zoom in really fast and write really small. So we would conclude. Sorry if your space is messed up like mine. Can you see it?
Yeah.
Okay. Conclude. What does our sentence start with? We are 95% confident, right? We are 95% confident that the interval from 49.09 to 88.61 pounds captures the true what? What's wrong? Am I going too fast?
No, Dylan.
Just Dylan.
Yeah.
It's just Dylan. True mean, what are we estimating? True mean weight of trash for all households in this community. Okie dokie. Do you see how it's really similar what we just did with proportions, if you can remember that far back? The back of 8.2. And let's tackle part A back here. This is the households about the trash. This is a means question, so we're going to use a different formula. Hardest part of this sometimes is just identifying am I means or proportions. So now notice this. The equation on your chart, it says n equals z star times sigma over e, right? And what else? Which part? The whole shebang is squared. All right, so it looks a little bit different, doesn't it? Now, didn't we say yesterday with means you have to use t? And proportions we use z? So why is this a z star? Inquiring minds want to know. So here's the kicker. Do you remember with t, you had to have degrees of freedom? What do you need for degrees of freedom? You need a sample size to determine that, don't you? And that's what the heck they're asking us to do. We don't have a sample size, so we can't determine degrees of freedom. So our best bet is to go back to a z-star scenario. Now, food for thought, one of these little details and stats. The only way you can use z-star with a means question is if you know sigma. Okay, z-star with means only if you're given The sigma. What is sigma?
Standard deviation.
Of what? Standard deviation of? Of what? Of the population. The standard deviation of the whole population. Okay? So it's a very unique scenario that you would ever use Z star with means. You just got to read your question real carefully and look for sigma. If it has sigma, then we're using Z star. Now, really the only time you're going to encounter this is in a sample size question. All right? So let's look at this. It says how many, do y'all remember this scenario? They want to figure out what the average poundage of trash is in a community. All right. How many households need to be surveyed to estimate mu at 95% confidence level with a margin of error of at most 3 pounds? So my margin of error, the E, is 3 pounds. Z star, okay, it's 95% confidence. This is what we were just using, right? That would be a 1.96. And then let's go back and look up at the beginning of the question. Does it tell us the sigma, the standard deviation? Yeah, what does it say it is? 36. All right, so now we have all our values to plug into our lovely formula. Definitely an easier one to solve for. Did you guys get 553.19? So that would round up to 554 households we'd have to check. Nobody wants to measure that many people's trash. For real? For real. Okay. So when you run across a sample size question, it's just identifying which scenario is it, proportions or means, and using said formula. Okay? Let's do this. All right. A Harris Interactive poll conducted during January of 2008 found that 944 of 1748 adult Americans 18 and older who do not have a tattoo believe that individuals with tattoos are more rebellious. All right. A says, obtain a point estimate for the proportion of adult Americans without tattoos who believe individuals with tattoos are more rebellious. So this gives us a hint, right? Find the point estimate for a proportion. So I'm looking for a p hat. Remember, p hat is however many out of the sample did whatever they're looking for. So what does it tell us? 944 out of 1748. Let's find out what that is. We'll call that 0.54. All right, B says, verify that the requirements for constructing a confidence interval for P are satisfied. Okay, what are the requirements or conditions or assumptions? Random sample. Was it random? Did they tell us it's random?
Good morning.
They don't say, do they? Okay, so we would say not clear. We don't know for sure, all right? All that means is I can do an interval. It just means my results may not be that accurate. That's all. And it may not be able to apply it to the real population. What's the other condition? Normal. How do I check to know if this sample is normal? It's proportions. Large counts. Yes, large counts. So let's do that. So 1748 times 0.54, which is what we had, was 944, definitely greater than 5. And then if I do it the other direction, I get 804 greater than 5. So we know that this is approximately normal. Done and done. It says construct a 90% confidence interval for the proportion of adult Americans without tattoos who believe individuals with tattoos are more rebellious. All right. So now we're at that confidence interval formula, right? It starts with what? Look at your charts if you're not sure. We're doing proportion, so it's the left-hand formula. Anyone? Huh? Thank you. P hat. I'm going to write the formula because we're having troubles finding it. P hat plus or minus Z star okay. So 0.54 is what we found as our P hat. Z star for a 90%. Y'all remember how to find it if I just tell you what it is? Good, 1.645, yep. 0.54 is 0.46 divided by 1748. All right, so now we got a number crunch a little bit. So notice on C, it just says construct the interval. It does not say interpret. If it said interpret, you would add on the sentence, we're 90% confident that the interval from blah, blah, blah contains a true proportion of people who think people with tattoos are rebellious, right? This one doesn't ask for that, so don't worry about it. Did we get that? 0.52 to 0.56? All right. Look at D. Construct a 99% interval for the proportion of adult Americans, same song, second verse. What's changing in my formula? Just the Z star. So 0.54 plus or minus 99 is 2.576. To get 0.51 to 0.57. So E is asking, what's the effect of increasing the level of confidence on the width? What happened? Did it get wider or did it get narrower? It got wider, right? Wider. And that goes to what we talked about. If we increase confidence level, interval gets wider. interval or the margin of error. That's really what's changing here. The margin of error gets wider. We good? Let's look at 12. Let's get through example 12 and we'll call it good for today. Dallas Stars active roster has 24 players on it. The average player weight in pounds is 200.2, while the standard deviation is 18.2. Assuming the data is somewhat symmetric, so that's helpful, right? That accomplishes the normal condition for us. Treating the stars as a representative sample of NHL players, construct a 95% interval on the average weight of hockey players. All right, so we've switched to means, right? So I don't think I mentioned this yesterday, but this is just my memory thing. I give students, use it or lose it, zap tax, okay? It's Z star with the P hats. It's T star with the X bars. Zap tax. You don't have to use that. But bringing up that we switched to means because we're talking average weight now, we're now dealing with a T star interval using the right-hand side of our formula chart, right? Construct a 95% interval. Okay, so that means I'm going to use this formula off my chart. X bar plus or minus T star times S over the square root of N. Now, every time you do an interval with means, you do have to calculate the T star. We don't have the same values every time because it's dependent on our sample size. Remember that? Okay, so let's just review for a sec. We want, how confident do we want to be? 95? So that means I'm 0.025 right over here. Degrees of freedom. What's my degree of freedom going to be here? Let's back up. What's my sample size? 24. So my degrees of freedom is 23. So let's find T star. Remember inverse T? .07. And then I'm going to plug in my values. They're saying we're going to use this as my X bar and this as my S. And I know that because it says we're using them as a representative sample of all the NHL players. So I'm going to use 200.2 plus or minus that T star we just found. All right, let's crunch some numbers. Do I get the same thing I got? Or just trust my numbers? Just trust me. Some blind trust there. All right. Okay, so there's the constructing part. Notice B says interpret the interval. How do we interpret an interval? We are 95% confident that the interval from 193.01 to 208.39 pounds captures the true mean weight of all NHL players. All right, C says, address the claim that the mean weight of all hockey players is over 195 pounds. Does our interval support this claim? Or no? Why not? Which means what? You're right. I just want you to put the words to it. Your thinking is correct.
Because 95 was over 193 because the elements. There's no way that all of them are over if our margin includes lower.
Exactly, right. Yes. So our interval contains values that are less than 195, right? Our interval represents the plausible values, what values are possible for the mean weight. So since there are values that are less than 195 in the interval, that claim cannot be true. Following here the logic? Okay, so what do I say? I just put that in words. Since the interval contains values less than 195 pounds, it does not support the claim. We do not have evidence for the claim because our interval has values less than. Then it says, address all the assumptions and the validity of your results. This is the conditions thing. Was it a random sample? What does it say back at the beginning of the question? What'd you say? It said to treat the Dallas Stars as a representative sample, right? Okay, stated. That's what I would say there. Representative sample would mean a random sample. Treat the Dallas Stars as a representative sample. And then what's the other assumption we have to show? Normal. Now our sample size is 24, so we can't use central limit theorem. But if you scroll back up, notice it says right here, somewhat symmetric, right? That is enough for us to say it's normal. We just need to reference that when we validate the conditions. So we would say, stated that sample is roughly symmetric. Okie doke. That's how you would work through one of those questions.